The concept of a slope refers to the change in height of a plot of a function relative to a change in horizontal location. There is no change in the value of a plotted curve at a single point. There is only one value, no change. Nevertheless, our eyes intuitively assign instantaneous slopes to individual points on plots of functions. The concept of a derivative uses a limiting process to bridge the idea on the one hand of a slope seemingly belonging to a single point with the idea, on the other hand, of evaluating slope by comparing multiple points separated by finite distances. After defining the derivative, we will derive formulas for the derivatives of composite functions, of products, and of the sine function. Sir Isaac Newton on the left and Gottfried Leibniz on the right are commonly considered the founders of differential calculus, which is, crudely speaking, a study of instantaneous slopes. Consider a function with plot f on x versus x. The function associates the point x equals x naught with f on x naught, and it associates the point x naught plus delta x with f on x naught plus delta x. We draw a right triangle with legs parallel to the horizontal and vertical axes with lengths delta x and delta f, respectively. The rise over run is delta f divided by delta x evaluated, and that's what that vertical bar means, evaluated, when the left-hand corner of the triangle is planted at x equals x naught. This is the difference between f evaluated at x naught plus delta x and f evaluated at x naught, divided by the length of the horizontal run delta x. This rise over run depends on the function under study. It depends on the location x equals x naught where we plant the left-hand corner of the triangle, and it also depends on the horizontal length delta x over which we allow the function to vary. We can get different numerical values for rise over run by, for example, considering values of delta x alternative to the length initially plotted. The ratio rise over run might approach a limiting value that we can determine by considering an unending succession of calculations with smaller and smaller, but all the while finite, values of delta x. This is read the limit as delta x approaches 0 of the ratio f on x naught plus delta x minus f on x naught, all of that over delta x. It is the definition of the symbol df dx evaluated at x equals x naught. This is called the derivative of f on x versus x evaluated at x equals x naught. It is the definition associated with a notion of an instantaneous slope at x equals x naught. The portions of this symbol, df and dx, are notated to look kind of like individual quantities. They are called differentials. They are not numbers. We will revisit this point at the end of this slide deck. Derivatives don't always exist. This plot is jiggly. It looks jagged even if you zoom in to small regions. We can choose to identify these 2 points separated by this finite horizontal run and draw this right triangle to calculate a rise over run. We are also allowed to choose other locations for the yellow marker. Some of the ratios of rise over run calculated using these intermediate points might be similar to the rise over run of the triangle outlined in turquoise, but some ratios of rise over run might be very steep and others very shallow. Even as the horizontal separation between the red and yellow markers becomes arbitrarily small, the ratios of rise over run explored continue to fluctuate wildly. They do not settle down to a well-defined single slope. This is an example of a function whose plot everywhere has no slope, and we don't mean to say that the plot has everywhere zero slope. We mean that the plot has everywhere no meaningful value of slope, not even the value 0. We will use the definition of a derivative to calculate the derivative of a quadratic function. This is the plot of the function whose association rule is f on x equals a times x squared. We want to calculate the derivative of the function using a succession of turquoise triangles with left-hand corner planted at x equals x naught. You might already be familiar with the result df dx evaluated at x equals x naught is 2 times a times x naught. Let's obtain this conclusion formally. Substituting the association rule a times x squared into the definition of the derivative gives df dx evaluated at x equals x naught is the limit as delta x approaches 0 of the ratio between numerator a times x naught plus delta x quantity squared minus a times x naught squared divided by denominator delta x. Distributively multiplying or FOILing the binomial turns the numerator into a times x naught squared plus 2 times a times x naught times delta x plus a times the square of delta x minus a times x naught squared. Cancel the plus and minus a times x naught squared. df dx at x equals x naught is the limit as delta x approaches 0 of numerator 2 times a times x naught times delta x plus a times the square of delta x, all of that over denominator delta x. And this factor is common to both terms in the numerator. Dividing this delta x out, we get the limit as delta x approaches 0 of 2 times a times x naught plus a times delta x. As delta x becomes arbitrarily small, the quantity 2 times a times x naught plus a times delta x becomes arbitrarily close to 2 times a times x naught. Thus, the limit as delta x approaches 0 of 2 times a times x naught plus a times delta x is 2 times a times x naught, as expected. The instantaneous slope for this plot increases or becomes more upwardly toward the right steep as the foothold for calculating slopes, that being x naught, moves farther and farther to the right of x equals 0. You might have been familiar with the derivative of the quadratic function because you had already memorized the power rule for derivatives. Do you know from where it comes? Here is a plot for a generic power law, meaning a function with an association rule f on x equals x to some power n. We want to use x equals x naught as a foothold for calculating the derivative of the function. The result will be df dx at x equals x naught equals n times x naught taken to the n minus 1 power. Substitute the association rule f on x equals x to the n into the definition of the derivative to get df dx at x equals x naught equals the limit as delta x approaches 0 of the fraction with numerator x naught plus delta x, that quantity taken to the n power, minus x naught to the n, over the denominator, delta x. Using the binomial theorem, the term x naught plus delta x quantity to the n can be written out as the sum from k equals 0 to n of n factorial over n minus k factorial times x naught to the n minus k power times the kth power of delta x. Consolidate stuff toward the top of the chalkboard. We write out the first two terms in the sum explicitly. For k equals 0, the corresponding term in the sum is n factorial over n minus 0 factorial times x naught to the n power times 0 powers of delta x. For k equals 1, the term is n factorial over n minus 1 factorial times x naught to the n minus 1 power times 1 power of delta x. The remaining terms for k equals 2, 3, 4, and so on as necessary to reach n remain collected succinctly in the sum from k equals 2 to n of n factorial over n minus k factorial times x naught to the n minus k power times the kth power of delta x. Cancel the first term and the last term, which are plus and minus x naught to the n. Recall that 0 factorial equals 1. Divide all remaining terms in the numerator by the common factor of delta x in the denominator. This means that the kth power of delta x in this red marker loop becomes the k minus first power of delta x in the next line. Because this sum starts from k equals 2, and the power on delta x is k minus 1, the powers of delta x that will appear, of course with additional coefficients, are delta x, the square of delta, the cube of delta x, and so on as necessary to reach the n minus first power of delta x. As delta x approaches 0, the sum, with the first term n factorial over n minus 1 factorial times x naught to the n minus 1, plus all of these powers of delta x, that sum becomes arbitrarily close to just n factorial over n minus 1 factorial times x naught to the n minus 1 power, which itself can be written out using the definition of a factorial in factors, descending in the numerator from n, and in the denominator, descending from n minus 1 and from 1. Cancel the many factors that are common to n factorial and n minus 1 factorial. The only surviving factors are n and x naught to the n minus 1 power, as expected. We have surreptitiously derived the derivative of a power law using the version of the binomial theorem valid for powers of n that are integers. If interested, you might wish to look up a version of the binomial theorem useful for non-integer powers and be glad to know that the mnemonic, namely, bring down the power n and subtract 1 from it upstairs, this mnemonic also works with non-integer powers. Not everyone enjoys routinely analyzing plots of function using definitions involving limits. It's slow. Now that we have derived the power rule, we keep it in mind rather than re-deriving it each time it appears. In practice, people might memorize a list of patterns, look them up from the physical pages of tables of derivatives, or use computational symbolic manipulation packages. Let's outline how we obtain some of these patterns, starting with the chain rule. This discussion, as well as those to come for the product rule and for the derivative of the sine, are only meant to be rough outlines in comparison to the derivation we have completed for the power rule. The chain rule is a pattern sometimes useful for simplifying derivatives of composite functions. Here's a plot of f on x versus x for some really boring function f. And here's a plot of g on y versus y, or g on f on x versus f on x if you'd like, for a slightly less boring function g. If x takes on the value at the base of this arrow, f on x is indicated by the golden marker. Draw a line to the corresponding point on the y-axis. G on y is the particular value that the function g associates with this particular point on the y-axis. Draw an arrow from g on y down to the z-axis. Arrows drawn in the xz plane point to a value of g on f on x associated with x. Exploration along the x-axis corresponds to exploration along the y-axis, which corresponds to exploration along the z-axis. We want to demonstrate the chain rule, which says that the instantaneous slope d g on f on x dx at x equals x naught equals the product of the instantaneous slope d g on f on x d f on x at f on x equals f on x naught multiplied by the instantaneous slope d f on x dx at x equals x naught. This is very painful to pronounce, and it is usually written and read dg dx equals dg df times df dx. If the animated markers explore intervals small compared with the geometric features of the plotted functions, then delta f over delta x might be close to its limiting value df dx, and so delta f roughly equals df dx times delta x. This delta f is the same as the delta f on the triangle next to the pink plot of g on y versus y. And again, since the markers are swinging across small intervals, delta g over delta f is roughly equal to its limiting value. So delta g is roughly d g on f on x d f on x at f on x equals f on x naught times delta f. Substitute here for delta f the expression for delta f from the preceding line to get delta g roughly equal to d g on x d f on x times d f on x dx times delta x. Dividing both sides by delta x, delta g divided by delta x is roughly dg df times df dx. If the plots of f and g are not too jagged, we anticipate that as delta x becomes arbitrarily small, the approximate equality becomes arbitrarily accurate, and also delta g over delta x becomes arbitrarily close to dg dx. Hence, the equation we wanted to demonstrate, dg dx equals dg df times df dx. The mnemonic for this rule is, derivative of a function with an outside and an inside is derivative of the outside times derivative of the inside. The chain rule helps us obtain derivatives for functions nested sequentially inside each other. The product rule is sometimes useful for simplifying derivatives of products of functions next to each other. A on x is the product of f on x and g on x. We want to calculate the derivative dA dx at x equals x naught, which is the limit as delta x approaches 0 of the numerator a on x naught plus delta x minus a on x naught divided by denominator delta x. We plot f on x versus x in the horizontal plane. The x-axis points toward the viewer, and the f on x or y-axis points to the right, slightly toward the viewer. We plot g on x versus x in a vertical plane. At x equals x naught, the values of g on x naught and f on x naught are the lengths of the edges of a rectangle whose area is a on x naught. Walking away from x naught and toward the viewer, we draw the rectangle at x equals x naught plus delta x, whose area, f on x naught plus delta x times g on x naught plus delta x, is a on x naught plus delta x. The difference between the areas is the total area illustrated in the light blue, green, and magenta rectangles. When we consider a limiting process in which delta x becomes arbitrarily small, we consider a process in which the light blue, green, and magenta rectangles become arbitrarily small. The light blue and magenta rectangles shrink on their vertical or horizontal edges only, while the green rectangle shrinks in both the vertical and horizontal direction. As delta x becomes small, the green rectangle could be said, in vernacular English, to be doubly small, and thus it is negligible while evaluating delta A. Delta A is then roughly just the area of the magenta rectangle with width f on x naught plus delta x minus f on x naught and height equal to g on x naught, plus the area of the blue rectangle with width f on x naught and height g on x naught plus delta x minus g on x naught. Divide everything by delta x. If delta x is small, and again the functions f and g have nice smooth plots without weird jiggles or jagged corners, we anticipate ratios of differences approximate derivatives. dA dx at x equals x naught equals df dx at x equals x naught times g on x naught, plus f on x naught times dg dx at x equals x naught. This is the product rule. The mnemonic is derivative of the first times the second plus the first times derivative of the second. For the quotient q on x equals f on x divided by g on x, what is the derivative? The solution has the mnemonic derivative of the quotient equals derivative of the top times the bottom minus top times derivative of the bottom all over the bottom squared. With the other rules already explored in this module, the reader can demonstrate this so-called quotient rule. And so we will not spoil the reader's pleasure in deriving this rule for him or herself. Instead, we close this module by looking at the derivative of sine. We previously introduced the sine and cosine functions as descriptors of geometry useful for talking about triangles and circles. These functions are also useful for describing oscillations in elastic materials in physics and in signaling networks with feedback in systems biology. Since triangles and circles are not necessarily obvious components of diagrams of vibrating piano strings or gene expression network cartoons, we need an alternative way to sniff out whether a mathematical model is amenable to simple expression or perhaps even solution in terms of sinusoidal functions. The derivative of sine is cosine and the derivative of cosine is negative sine. Roughly speaking, the sines and cosines have an interesting property that they quickly come back to themselves upon successive differentiation. F is now the sine function, with the association rule f on theta equals sine on theta. Substitute this association rule into the definition of the derivative. df d theta equals the limit as delta theta approaches 0 of the fraction, with numerator sine on theta naught plus delta theta minus sine on theta naught, all of that, over the denominator delta theta. Using the angle addition identity for sine we previously reviewed in the module on Euclidean geometry and trigonometry, we rewrite the term sine on theta naught plus delta theta using the mnemonic sine cosine cosine sine, or more slowly, sine on theta naught times cosine delta theta plus cosine theta naught in yellow times sine of delta theta also in yellow. Everything else in the equation is untouched. Collect the terms formatted in white font in the numerator so that they read sine on theta naught times the quantity cosine delta theta minus 1. Then split the limit into two pieces. The limit as delta theta approaches 0 of sine on theta naught times the ratio cosine delta theta minus 1 over delta theta, and the limit as delta theta approaches 0 of cosine on theta naught times the ratio sine delta theta over delta theta. Move that equation up for space. We need to know what happens to sines and cosines as delta theta gets smaller. Draw a right triangle with hypotenuse of length 1, meaning that we are sitting on part of a unit circle. Here is the arc length delta theta. The length of the leg opposite the turquoise label for angle delta theta is sine on delta theta. As delta theta becomes arbitrarily small, meaning as the triangle in blue becomes arbitrarily slender, the length sine on delta theta and the arc length delta theta become arbitrarily close. The ratio sine on delta theta over delta theta goes to 1. The length of the leg adjacent to the turquoise label for the angle delta theta is cosine delta theta. Since this leg does not quite reach far enough out from the center of the unit circle to touch the circle, there is a gap of length 1 minus cosine delta theta so tiny that we need to highlight it with an animated arrow 5 times. Please stare. As delta theta becomes arbitrarily small, as the big turquoise triangle becomes arbitrarily slender, the length 1 minus cosine delta theta in green becomes arbitrarily small relative to the arc length delta theta in orange. The ratio of cosine delta theta minus 1 over delta theta goes to 0. Thus, df d theta at theta equals theta naught equals cosine of theta naught. The derivative of sine is cosine. The derivative of sine is cosine. Is this plausible? Plot sine on theta versus theta and cosine of theta versus theta. We will track sine theta and cosine theta around the unit circle. Wherever the turquoise curve is steep and climbing, the gold curve should be positive. Where the turquoise curve is descending, the gold curve should be negative. And when the turquoise curve passes through a peak or trough, the gold curve should pass through 0. From knowing that the derivative of sine is cosine, we can determine that the derivative of cosine is negative sine. Why? Here's one way to begin a response. Consider the right triangle with angle theta, or just as well with angle pi over 2 minus theta. The leg that is adjacent to the label for theta is also the leg that is opposite the label for pi over 2 minus theta. Hence, cosine of theta equals sine of pi over 2 minus theta. The leg that is opposite to the label for theta is also the leg that is adjacent to the label for pi over 2 minus theta. Hence, sine on theta equals cosine of pi over 2 minus theta. You may check the plausibility of these identities using the plots of sine and cosine on the preceding slide. Derivative of sine is cosine, and derivative of cosine is negative sine. Derivatives of sinusoidal functions, in a sense, come back to the sinusoidal functions. Some of today's outlines, for the derivations, for the chain rule, and for the product rule particularly, made use of squishy words like approximately or roughly. We associated imprecise meaning with notation, including the approximately equal sign or the equal sign. This was in contrast to the style used for derivation of the power rule or for the worked example of the limit of a linear function from a previous module. In those cases, we used equal signs when we intended. In physical applications of calculus, notation and speech are often sloppier than even some of today's outlines. You can get away with doing a lot of mathematical modeling with the squishy geometric notion of words like relatively big, relatively small, or doubly small. One place, however, we must establish boundary conditions for safe practice is the vocabulary term differential. Patterns of letters like df or, for example, dx are called differentials. In this course, we will regard differentials as syllabic components that are said to be part of meaningful contexts only when combined with other syllables to form words. In this course, the pattern df by itself is meaningless, but written over a bar over another differential syllable dx, with the entire fraction-looking symbol pronounced as the one word df dx, This df dx has meaning as the derivative of f with respect to x. We will find later that the syllable df can also be part of a meaningful structure when paired with another symbol, the smooth s, which looks like the sound hole on a violin. In this course, we regard isolated differentials as no more meaningful than isolated syllables torn out from words. As we move on, differentials will soon look more and more on paper like bona fide numbers. But if we start out from day one pretending that differentials are numbers, we can run into a lot of confusing problems. Differentials are not numbers. df is not a number. dx is not a number. dx is not at all a number, not even the number 0. Paired appearances of the symbols df and dx, such as in df dx, refer to an unending process of studying successively shrunken but all the while finite numbers delta x, with the corresponding collection of numbers delta f, which themselves could be finite or 0. Think of differentials as shorthand for limiting processes rather than as literal numbers. Here is one example of a finite number delta f and a finite number delta x. As we explore smaller but always finite horizontal separations delta x, we enumerate other numbers delta f. If the ratio of delta f, now delta f is a number, to delta x and delta x is another number, if that ratio itself becomes arbitrarily close to a limiting value, then that number, which no delta f over delta x necessarily ever achieves, that limit is called df dx. Paired appearance of differentials is a good reminder of a notion of paired shrinkage of finite quantities. If you find a line of derivation in calculus apparently notating df on its own, so to speak, you might try to look around nearby for a corresponding symbol that looks like dx, or at least an implied notion of paired shrinkage. Regardless of how closely we look, at least in this course, we find no tick marks on the number line corresponding to df or to dx. Differentials are not numbers.